like force sensor array, for example, and trying to, because I already did it, I use different matrices from FSR technology, and I use compliant materials. In the it's the same approach, and of course there is hysteresis. You have latency. So, did you evaluate with the VAS sensor from
the dynamic response? You say?
Yes.
No, in the dynamic. The response of the surface itself we didn't evaluate, and because we assumed the quasi-static case. However, the sampling rate of such a sensor is only 150 Hz or 200 Hz, and I limit it up to 100 Hz. And all the controller loop of Tactile Stereo works on 100 Hz, and this is enough to perform such kind of tasks.
Okay. I have also one question, because can you tell me what about the frame rate for the video? It's not real time, because what is the scale factor for the time for the video?
4 times.
Yes, okay, I prefer, because
the real one here is shown when the end effector is moving slowly along the bar, but yes. Here there is no scale of the frame rate of the video.
Yes, because of course it's very impressive work, but one essential question is if you want to provide interaction, dynamic interaction with our environment. Of course, it's quasi-static case, but it's important to be able to increase the dynamic of the whole system.
For that, we need model predictive controllers.
Don't you think you could, with such an approach, increase the dynamic, because the system, the communication with the robot is 1 millisecond for the communication between the HEVA and the controller. If you have a real-time controller, I mean it's about 270 Hz for the sensor bandwidth. So I mean you can increase the dynamic of the response.
Yeah, I have one video.
With the same approach, I mean.
So with the same approach, I increased the PID gains of the end effector, of the PI regulators.
Yes.
So we can perform even the manipulations during the interaction with the human. This video.
Yes, because you have, as you said in the presentation, you have a block diagram for the hybrid tactile position controller, and in the diagram, of course, if you want to adjust the response and the way how fast the tactile controller will regulate to 0 the desired feature, you have to you use the gains KP and KI. I think you have about 12 coefficients, I mean, 6 KP and 6 KI, is it true?
So there are, yes, so for each feature I have different KPs.
Yes.
And
so I mean it's about 12 gains, 6 KP and 6 KI, it's true?
Yes. Sure.
So do you change the gains according to the task? I mean, if you make an exploration task, do you have a set of gains? If you do another task, do you have another set of gains in order to adjust the response, in order to take into account the task you do, or do you always?
For most of the tasks, I do not change, but for the task that can
for the exploration, I mean you have changed, no?
Yes, I've changed those gains for exploration.
Yes, of course.
But here I can set those gains high so that the end effector reacts to the human movements quite fast enough, so the end effector is able to explore some bar as is during when I'm changing it in real time, and this video is not changing the frame rate.
Yes.
But it was quite dangerous.
Yes.
That's the
thing. Can you tell me what about the delping and stiffness coefficient for the KUKA robot you use? Is it only
yeah, it was set in we use the Cartesian impedance controller of a KUKA arm.
Yes.
With the default stiffness and damping parameters.
Yes, and how did you choose damping and stiffness coefficient for the HEVA robot? Because I mean, in your document, you used to say that maybe passive compliance, of course, is a problem because as the surface of the sensor is compliant, so if the compliance from the robot, the passive compliance from the robot is bigger than the compliance of your sensor, it may be a problem for you.
Yeah, it may be a problem, but it was tested that when actually there is an interaction with it, I'm not controlling the force. Yes. I'm just set the end effector to keep the same stiffness damping parameters, and we were pressing the sensing surface.
Yes.
And due to these changes, the end effector pose itself does not change. So the stiffness parameters of the end effector was chosen to be high enough in order to not take into account the compliance of the sensing surface of the sensor.
Okay, yes. Very good. Will it be a problem with the
shadow
hand? Yes,
yeah, it was a big problem.
Yes.
Honestly, when the shadow hand, first of all, the sensing surface was only 50 by 24 millimeters, and when we are controlling the shadow arm with the pneumatic actuators, the precision is not. Sometimes it flips away from the sensing surface, and comes back. But it's usually suggestible to switch off the controller when there is no contact. So the tactile controller doesn't work when there is no contact.
I think that's why it's a good solution to have the HEVA robot, because you can adjust damping and stiffness coefficient for the robot's position control of behavior.
Yeah, and moreover, during those work with the KUKA arm, it was assumed that each new pose sent to a robot is actually the actual pose in the next cycle.
Yes.
We are not, because at the beginning we were like assuming, okay, we can read the pose each time. However, the robot goes to its torque limits.
Yes, because there is something that lacks in the report. It's the whole control architecture, because I guess that there is a PC. Maybe with not real-time PC, but maybe a PC with Oracles for getting the acquisition of the sensor using USB, or maybe, yes, I think it's USB communication between the sensor and the PC, and you have maybe Ethernet. Okay, very good.
Yeah, I had this, but without the KUKA arm. Yeah, this is for the shadow hand.
Yes.
So I had this structure for the shadow hand because this is for future work with the tactile scheme from CEA.
Because what is difficult in the wall communication, if you want to have a good robustness for your wall control of the system, so it's not really a problem because the timeline is very low. So each task requires about between 10 seconds and 20 seconds for executing. So it's not really real time, but if you want to increase the dynamics, what will be very important is to have a good control architecture with real time communication. So I mean, not really with high dynamics, but it will require the same baseline, the same clock for the whole system. So you can't have it with such an architecture because you have UDP, a PC, you have a sensor on it.
For that, maybe with ROS2. Which is a software real-time environment. It's going to be kind of real-time. But with ROS, it's not.
We can observe this on the, for example, on your slide 17 or on the slide 30. When you look the curves, there is a difference between the ATI sensor acquisition and between the sensor acquisition. The tactile sensor acquisition. There is still a big difference.
Yes, there is, and it's only because the real measurements that are provided by ground truth force torque sensor, we somehow tune to the piezoresistor sensor to have the same values. However, they always change due to some creep behavior, temperature variations. So it's only the proxy of the real forces.
So do you need to make a calibration each time you use the sensor? Because it's very important. What about repeatability, for example?
Because here I have this repeatability curve. Yeah.
Yes.
So repeatability is it's still those piezoresistive or capacitive sensors are still far from ideal behavior. And the repeatability. Here we have the curve. Here, the same tactiles were pressed with the force torque sensor. Here, so the real force, ground truth force, this is sensor output. The same tactile pressed several times.
Okay.
So the change, I don't remember, it was 1.5 times of the amplitude.
And in your simulation, as discussed in the document, page 42, you present the simulation environment. Did you integrate the fact in the simulation that the sensor sensitivity is not the same in the center of the tactile sensor and also on the sides of the sensor?
No, this sensor in simulation was assumed to be ideal, but also in Gazebo simulator using the Open Dynamics engine, it's impossible to simulate the deformable objects.
And in the real controller, did you took into account the fact that the calibration takes into account the fact that it's not the same?
It's possible to create even in the low level this matrix that will always take into account those changes. However, the forces that were applied to the environment were in that range, the linear range. I assume that it's a linear range, and with the PI gains, they were they converged. It was enough.
Okay.
It's possible to make very precise calibration of those sensors, but it takes like a week, maybe for each tactile, because there are temperature changes, and then due to the tear off, each time we manipulate an object, the surface
so it may be difficult to use this kind of sensor in industrial environment where the temperature changes. You have to regulate the temperature in the room if you want to use this kind of sensor. Is it the same for the sensor from CEA? Do you have the same behavior? Did you evaluate the sensor from the CEA as you evaluated this one?
No, only the dynamic response we evaluated, but not on the hand itself. I think there will be still a lot of noise because the hand is electric motor driven. There is electromagnetic compatibility. The capacitive sensors, they actually sense the charge.
Yes,
and this would create, I guess, some.
But what I had problem with capacitive sensors in the past for this reasons, of course, because it's very
with these new sensors in ECA, they're using the coaxial cables and creating the shield.
Yes.
By that, I hope we can avoid this electromagnetic.
Yes, it may be better. Yes, of course. Just one, maybe still a little time. Just maybe 5 minutes. Just one question concerning the response for the sensor and the validation for the response for the center of contact. It's not the same response in the frame, in the tactile frame, in the contact frame. You should maybe have the same kind of response in the X direction and also in the Y direction. But it's very clear for the X direction. What would have been interesting is to have the same scale and the same amplitude for the motion.
I discussed it there, yes, because we can have some trajectory layer where we compute the trajectory for the convergence along X-axis and along Y-axis by taking into account that the sensor size is different. That's why we can tune the PI gains in order to converge the error at the same time. They do not converge at the same time. It's like
Yes, but it's strange because it's really a very good response in the X direction, but it's really not a good response in the Y direction. So you think it's because of the gains?
Yeah, it's only because of the gain, or we can add the trajectory calculator. So we calculate by knowing in advance the error in X-axis and Y-axis. we can set each new desired center of contact so that the error converges at the same time. It's like closing the hand at the same time. We can compute the joint angles so that they come to the contact at the same time instant.
So thank you. I don't want to take all the time, so maybe I'm going to make my colleagues to achieve. So thank you again for your presentation. Maybe just one last remark or question. I think it's very important to choose the good material at the top of the, and your approach is really based on the behavior of the material you put on the surface of the sensor. So I mean, one of the key of the success for the future use of the CA sensor is maybe the way you will choose the material.
So with the 3D printers, nowadays 3D printers, it's possible to print rubber-like material, and in CA they have it, and we are going to change different structures, bulbs, or just flat surface printed using this rubber material 3D printers, and then find the good layer for that, yes. And using this rapid prototyping technology is easier now.
Okay. Thank you very much. Thank you very much.
Give the floor. Thank you for your response to your other reviewer, Professor Youssef Mizouar from Sigma Clermont.
Okay, so thank you. So first I would like to thank Véronique and Juan for this invitation. I was very pleased to read your document and now to see your presentation. So it was very nice to see the work you did during these three years. And I appreciate the different contributions. I think there are 4 contributions here. There is the first one is about maybe the bibliographic part, which is very nice, and I think would be very useful for new PhD or new worker on this way. I would say the experimental validation, which is very impressive. So I appreciate this part because in robotics we always want to see the things working. So this was very a good thing in your manuscript and also in your talk. And I would say two methodological contributions. The first one is how to design good tactile features for control, and the second one is the control itself. So I have Jean-Pierre asked many questions, so but I have always some questions. So the first one is about you answer to Jean-Pierre that the best sensor for you will be the Biotac. Yes.
Because they sense vibration and we can do research on that. Okay. As for example, vibrotactile based control. When we actually map the vibrations to the velocity, which is interesting.
But my question is how you can adapt your work to this sensor, because the distribution of tactile is not regular, and also I would say this is not a planar also sensor. So do you have some idea to general, because you say that one good point of your work is that you have an approach which is generic in terms of different type of contact, different type of task, but yes, it will be also, I think it can be also generic in terms of sensors. But for this special case of Biotac, there is some difficulties.
Yeah.
No?
First of all, we can vice versa the problem itself. We can solve inverse problem. So Biotac is a cylindrical object, or we can assume spherical, and we assume that the surface is a flat, yeah? And there is a contact between the spherical tactile sensor with a flat environment. And we can sense the center of contact point on the sensor. And by controlling the center of contact inside this tactile array interacting with this environment, we still can apply this tactile ceroing framework where we map different. So here we can map center of contact, yeah, that we calculate from the Biotac sensors to the rotational motions of the fingertips using this projection matrix, yeah. And then if there are several of these tactile sensors on the fingertips, then for each finger we would have this the tactile controller, and then we can still can control these features in order to perform some different tasks applied to the environment.
Yeah, this is one point, and the other point is about the non-regular distribution of tactiles.
Yeah, we can.
Because in your
So first of all, this is the baseline. We can actually take this biotactile sensor, which is cylindrical, spherical, and assume that all contact points are in the flat. So we do the manifold. We project this manifold to the planar surface. So the whole fingertips will have the two-dimensional representation. And then we can compute the center of contact.
Okay,
that's
nice.
it. However, there are more interesting studies conducted by Montana or Furing, where the contact mechanics are considered, but it's more about the elasticity theory, the mechanics itself, and where they calculate the tensor of the contact.
Okay. So also, I think Jean-Pierre also asked you about the calibration of the sensor, and I don't see exactly where you use the calibration inside the control loop. Where is exactly if you can show me the scheme of your control, the scheme of your control, and where is exactly the calibration?
So we
parameters?
calibrate once before task. Yeah. So each new day I did a new calibration, because for the second day it could be.
No, but my question is about where it appears in the control scheme. Okay. I think it appears only for the force. F.
So it appears only for the force
F.
and the moment of force, the MP feature.
But you never use it because you directly compute the crystal level. You compute the DMP with
Pressure
the
values.
Yes, but using the tactile image, no?
Yes, tactile image. Yes.
And here you use the.
So I do not apply the. No. There is a gain, the proportional gain for force. For instance, here there is a sensor output and the force, the ground truth force measurements. In order to somehow match them, I multiply it with the gain. And for the ZMP feature, there is also gain.
Yes, but why you need this?
In order to
because your reference is also.
No, if the tactile sensor wouldn't be calibrated well
Yes.
enough, I would crash the environment or the robot.
No.
That's why it's important to have a.
No.
Yeah. Okay. So if this the controller can actually react fast. If there is a too high gain, the controller will be. The controller gains can be tuned so that the stiffness parameter would be lower. Yeah, it can be taken by controller. However, at the initial contact phase, it can apply too high force.
Yeah, but if
the desired reference, if the desired force would be would have too high force, then it will break the environment. Because it will not represent
the
actual
reference, but you have to choose correctly the reference.
So the reference is very important to choose them correctly.
Yeah. So my question was about, you can show maybe the image feature, the 6 component of the image features.
Mm-hmm.
Yes, someone. Yeah, this one is okay.
This one, So here, it's important.
Yeah.
So the moment of force is controlled here, to 0.
Yeah, but you see the third coordinate F. So this one is need the calibration.
Yes.
But
this one also the calibration is needed.
Okay, so this is outside the control loop.
Yeah, inside the control loop.
No, outside, because this is the measure. No.
Yes. Okay.
It's not directly in the control.
Yeah. It's not there is no dynamic calibration. That's the thing. Yeah. So there is no auto calibration.
Yes, but my question is,
It's
for me, if you have only a linear coefficient here, in F or in the other, because you assume that this is a linear relation between F and your pressure.
Yes,
I'm
which
right?
is not linear. Yeah. Yes, it's a third order polynomial.
Okay, so maybe it will be pretty easy to show that even with error on this coefficient, you will be able to control the system correctly. Because this is only a coefficient a linear coefficient on your measure.
Yeah. Okay, so if the controller bandwidth is high enough, yes, though any non-linearities can be taken can be compensated. If our sampling rate is really high. So, for instance, if there is a really non-linear system and we are controlling it at a high frequency rate, those non-linearities are linearized because we control at small time intervals.
Okay.
It's like when there is a water tank inside the non-linear shape, and we want to control the level of the water inside this non-linear shape. If our controller is fast enough, we don't have to model all the shape, all the volume of the water inside the tank to control. We can just control the level where we measure it without knowing the model. And if the controller is bandwidth high.
Okay.
But yeah, the real response of the tactile sensors are not linear yet.
Yeah, because so my remark was in your features is your features can maybe directly be computed from the image, tactile image.
Yeah.
And compare it to a tactile image, and there will be a scale there with respect to the control, the pose. But this scale, I feel that it will not influence too much the stability of the whole system. But I don't know if you do some experiments with bad calibration.
No, but it will be interesting future work for the to perform the control without calibration of those sensors.
Okay.
And there are approaches using neural networks even in order to control the robots without calibration.
Yes. Also.
It's like learning maybe affordances. Because when a robot is pushing some object and then it sees the response, it can learn what actions can be performed on that, or it leads to which consequences. So.
Okay. So yes.
It's like take maybe torques. We can measure torques of a robot arm and push some static environment with the tactile sensors, and then we do online calibration based on the torques we apply, and we estimate the force applied at the end effector.
Okay. And what is also your feeling about the error measurement error on the center of pressure and center of contact?
So what is the difference?
What will be the impact of because you see in this image we see that this is the tactile are pretty. I don't know the resolution of this sensor, but the tactile is pretty big, no? And we can have measurement. We can change the measurement very fast enough. We can pass from one tactile to another one if you are in the limit. If the contact is in the limit of tactiles, no? And so you will have discontinuous measure.
Yeah. So yes. So two neighborhood tactiles. Then you can switch quickly. This can be smoothed by median filters or Gaussian filtering. So by applying point spread function. However, the elastic surface itself of the sensing sensor does this for us. It acts as a low pass filter That's why those changes from one tactile to another are smooth enough. They are not discrete.
Mm-hmm. Okay. Yes, I have other question about control. You called so there is a Jacobian.
Jacobian.
Yeah.
Which is
yeah,
not
this one. So. Yes. Yeah. Yeah, this one is okay.
In the tactile serving,
Yeah.
Together, the projection matrix with that inverted the Jacobian matrix is mapping the feature error to the contact frame errors. Yeah, that's why it's called tactile Jacobian, because error are mapped to error. But it's not a real Jacobian as in the robot arm control when the changes in joint angles are mapped to some other space, which is Cartesian space. However, this is a feature space, that is a contact frame space.
And this is not a Jacobian.
This is the interaction matrix, I would say, as in a visual serving approaches. However, this can be considered as a Jacobian because if we take it together with the, so using the stress and strain analysis, yeah, when there is only surface deformations are considered, and our tactile image represents those deformations. If we avoid all this projection matrix and the inverse tactile Jacobian, yeah, considering directly the physical deformations of the sensing surface, yeah, the mechanical structure of itself to the contact frame, this is a Jacobian actually.
Not for me, not exactly, but yes, can be maybe.
There are different parameters that changed inside the.
Yeah, because the Jacobian should be the derivation of the.
There are derivatives
of the features. But this is not clear for me. And the projection matrix, this is the selection matrix, no?
No, it's also a selection, but at the same time, in order to perform the co-manipulation tasks,
yes.
It maps one feature error to another Cartesian space error. So this is also like projecting. It's not only selecting. We project one feature to directly another.
Okay, but how do you manage, because you change the coefficient of this matrix during the task, they can change during the task?
Okay, so for the, yes, in order to start the exploration, so as soon as the end effector is, for instance, aligned with some edge, it can start the exploratory movements. So the projection matrix, set this in motions.
Yes, so you have to change the coefficient of the.
The coefficients are changed. At the
But
time
how
we change.
you do it in practice? You change this coefficient. So before the task, you say that no?
Yeah. So we assume that in advance we know our affordances. That's why in advance we set this gain to be equal, for instance, 1, in order to start those exploratory movements. It's known in advance here. It changed online.
And when do you?
It's changed as soon as the edge contact is detected, and then it starts sliding.
Okay. So
we can actually program in advance, hard code these exploratory movements, come to contact, align, and move. So it's hard coded in advance.
Okay. And do you think it is possible to manage this online? That is to, if in the real world you will not know exactly the task, and you will have to change the coefficient of the selection part of the matrix.
Yeah, for instance, if there is some disasters in the Fukushima, where the plant explodes, and I know that in such kind of conditions, vision sensors, they don't work well. And in such kind of environment, the tactile sensors would be the only feedback about the environment. No?
Wrong. No electronics.
No
It's each week we have electronics, so it's not true.
Well, there are cases when the vision, actually, okay, in some industrial manufacturing, there are cases when there is a steam between a robot and the object to, for instance, clean. and vision sensors also fails under that steam. And the only way would be they interact with that object and perform some cleaning tasks.
But yes, but my question was more about how to predict, to change the selection matrix during the task, because you do
for
it,
that,
but
it should be
you
one
planned
more
this before.
higher level with learning algorithm, where the affordances would be learned in online. So when the object first, okay, will try some action, see the output, get some rewards or some errors. Based on these rewards, it can learn the new actions to perform over that.
Okay. I have a question also in this slide. It's about your feature error vector. So this is a difference between the two vectors, yes. But one is directly
This desired vector given by the task, which we know in advance.
the fourth and fifth and the sixth also coefficients are directly linked to rotation. Yes?
Yeah, here?
Yes, no, in your feature error, you see if you have in the general case.
General case, the first vector.
No, in this vector, the fourth entry.
The
fourth.
No, if the projection matrix would have the.
No, I will see the three entries related to rotation.
Yeah, these three, the last.
The last three, yes.
Yeah.
And you directly do the difference.
But not always in the co-manipulation task. This feature is projected to the translational motion.
Yeah, okay. Yes.
That's why this is not only selection matrix. That's why it's only
okay. We change with this.
Yeah. Afterwards, in the next slide, I show that those errors, even the map directly to the rotations, but they can be projected to any other error in the Cartesian space. So besides the switching between different features to control, we switch between the different actions. Yeah, that's it. So,
okay.
For instance, when this projection matrix here, first element is 0, a robot can perform alignment with the bar. And when it's ready to begin the motion, it just the end effector sets in motion along this xy.
Yes, but you see for the three last one,
the rotation always.
They are linked directly to rotation. Yes.
Yes.
So it's just a small remark, but in this case, maybe should be better to have a different error, the difference between the two rotation.
Okay.
Because you use the difference between angles. This is linked with the scale factor. There is angles. This is right only if you have small rotational motion. But if you have bigger, this work here because you have small rotational motion. But if you have bigger one, this error is not.
Using the that's true. When there is a big error for it's always problem for the rotational errors. If there is big error between two different rotations,
it's a difference between the angle, not sure.
So that can be problem. For that, again, the trajectory can be computed. So the error between two different angles first can be analyzed by some upper level algorithm that computes trajectory. So the trajectory can be computed in order to rotate around one of the axes.
So there is way to define the error for rotation.
And also the quaternions can be taken in order to control them.
Okay. So let's see if I have something.
It's more interesting also to define one more feature, the seventh feature, as in the visual surveying when they directly map the quaternions and the feature errors in the visual image space.
This is possible to use something like that. Okay. So for me, I have no more questions. So congratulations again for your work.
Thank you very much. So now I I will give the floor to Professor Gaspar Altofleur
Many thanks to the
from
chair.
Queen University.
Yeah, okay, yeah. Thanks for giving me the opportunity to be here and also to give my comments. And also thanks to Veronique and Juan for having me here. Yes, as it was said already before, it's always nice to come to Paris and see you and see what's happening here. And I can only kind of repeat what others have said already. So very good work, fantastic work. Congratulations for that. I was very nice to read, and lots of stuff has been done, so fantastic. And you have tried already to summarize your contributions, and I think I agree with what he said. Possibly what you have done goes even beyond that. The issue I see, so maybe now I start with my negative comments, that you don't express it properly. I looked in your thesis, and so you have your contribution summarized on page 5. You don't say all these great things that you have done. I don't know, is that proper for that to be corrected? Or?
Yes.
Okay. So I would highly recommend that you go back there and look at what you have written and to see whether you can prove that. I think in your presentation you will summarize it much better.
Yeah, the unified framework, driven manipulation, and
I come to that, but your ZNB approach and then the controller. So these are the main contributions, and principally to talk about that. Yeah. So tactile feature extraction, yeah. And then the tactile Jacobian, if we call it a Jacobian, yes. And the projection matrix, also that kind of links to the tactile Jacobian, I think. So we speak a lot about the unified framework. So what is this unified framework? Because it was not so clear to me.
so it's about the task layer, where different tasks as a recognition of the objects by squeezing those objects doing exploration. We don't have to switch between the tactile controllers. We don't have to change the controller to perform those tasks. That's why it's a unified approach. And we defined many different tasks with their descriptions. So we defined the task descriptor in order to perform.
And by tasks you mean like exploring, like following a line? Or?
By task, I mean applying some force, apply the force that follows the square wave function in order to recognize the probability of object. Or do manipulation and explore shapes of, like reconstruct the shape of an object from the manipulation. So for that we also define the desired set of features and then offline algorithm to do so.
Okay, so the unifying aspect is that you use one sensor to identify the object and to exploit?
One controller.
Yeah,
one
controller, yeah.
One controller, one sensor, one arm to do different tasks, yeah.
Okay. With one object. And with other objects as well.
Yeah, with other objects.
Yeah. But it's so the unification is that you apply different robotic tasks, as you say, to the one object. So you can reach it and you can explore it, or is it about doing that to one object and then to
no, we can do it to one object, yeah, to manipulate or press. That's one thing about the unification, but it's also about the different objects, different environment conditions.
Okay. Good. Okay. Yeah, I mean, I'm happy with that. I just have the feeling it's a bit of an add-on. It's not sitting really in your contributions there.
Unified.
Yeah, because but what you told me now is interesting, and I agree that's something you have done and it's described here. But I haven't, in my mind, really explored to what extent that is an important feature. I don't know, maybe it is, yeah, but in any case, I would then have that as an extra bullet point. So the other 3 points, now it looks like that is under your unified framework, but that's not what you're saying.
say, if I would add
they
revision.
are part of it if you want, but because your tactile feature extraction can stand by itself, it doesn't need to be part of your framework. That's what I mean.
Yeah.
And also your controller is independent of your unified framework. So in my mind, the unified framework, what you understand under the unified framework is actually a separate point. That's the way I would say. So you have your feature extraction, you have your controller. I think the tactile Jacobian goes together with the projection matrix. And then you have another point where you say, now I can also do this very clever exploration of the environment. That's the way I would kind of call it, but not, I wouldn't call it a framework. I don't know. But that's what confused me a bit. But coming back to my earlier point, so I would recommend to go back also again and to say these things that you have done in your contribution list. For example, you don't speak about a ZMB feature, and you don't even speak about tactile feature extraction. You propose new tactile features, but that's what you say there. But I think it needs to be reformulated. Now, coming back to those features, so you can extract points and lines, and also the new bit is to have now these lines that are interrupted or not across the whole area, and maybe at a certain angle with respect to your sensor.
Partial.
Yeah. So I think these are the important points. The final one is an important point because the other things have been done before and already. Point extraction and line edge extraction. But again, I think that needs to be also highlighted. What is really the thing that you have contributed